Okay, so just the main point from last time was we were looking at the system of axioms for the integers, and our main focus then was on the axiom of induction, or if you like, the principle of proof by induction, because as we emphasized, this is what really separates the integers from the other rational numbers and the real numbers, which share all the kind of common algebraic properties that the integers have. So if we're going to be studying the integers in detail in this number theory course, a lot of it is going to turn on this principle of induction, and we'll be looking out for the key important things through the course which are based on induction. Okay. Now, last time we were practicing this principle on a number of these exercises here, going from this. Just usually the first example of induction, you see this formula for adding up all the integers between 1 and some upper limit. It's a nice quadratic equation in the upper limit that gives it to you. And we did a few of these other ones, I think, in class as well. And in the tutorials this week on Friday, we'll have time to kind of tidy up any remaining problems with those. And if you haven't already, do have a go at the later ones, and especially these inequality ones. The inequality ones do take a little bit more puzzling out, because when you're in the middle of these exercises here, 3, 4, and 5, say, what you're trying to do in the difficult in the induction step is to build a chain of equations. In some ways, building a chain of equations is maybe a bit easier than other types of problems, because although you have to figure out what the correct transformations are, but you're pretty limited. There's a pretty limited scope of possible transformations you might do, because you have to keep it an equation. You can only pass to something that's equal to the previous thing. Whereas when you're in the middle of these proofs here, you'll typically be building a chain of inequality. Well, maybe some of the links in the chain will be equations, but then the other links in the chain will be the appropriate directed inequality. And that immediately is maybe a little bit harder, because there's a lot more choice involved. If you want to pass from some object to a smaller object, there's a lot more freedom. You know, you could take off a huge bit, you could take off a tiny bit, make it a bit smaller. So, and judging what the correct thing to do is maybe a little bit more subtle there than in the equation case. So do keep working on those this week. And we may also look in the tutorial at the solution of this issue as well, although this is something you could maybe look up during the week. But I might do one or both directions of this, okay? Because remember, there was two. So this is axiom 11a is equivalent to axiom 11b. These were the two versions. Well, the two ways of phrasing, the two ways of presenting this last axiom for the integers. You got the induction axiom, which is 11a, presented in a slightly different format there, talking about membership of the set, but still you'll recognize this as being the induction principle. And 11b fits this statement, which at first sight looks quite different. And it says every non-entity subset of the positive integers has in it a least element. Okay? Not true for the rationals or the real numbers, because you can have sets of positive rational numbers which there is no least element. For instance, a set of all rational numbers greater than something. Set of all rational numbers greater than 1. The set has no least element. So the well-ordered axiom is not true about the rational numbers, but it is true that it turns out these two principles are actually equivalent to one another. So if you assume one, you can derive the other, and vice versa. If you assume the second, you can derive the first one from that. So we'll also have a look at that in the tutorials. Any remaining questions then before we move on to chapter 2? So, any points from chapter 1 you'd like to raise? Okay. So chapter 2 is where we start to meet then some of the concepts we'll be dealing with in detail. And really what we're gunning for here, what we're on our way to, is the definition of prime number and building up the theory the basic theory about facts about prime numbers. Before that, we're going to very carefully introduce the notion of divisibility. So divisibility is a binary relation on the integers. It's a logical statement that takes two inputs, and it gives you a statement that's either true or false. So it's a relation. It takes two inputs, doesn't give you another number, it gives you a statement, and that statement is either true or false. Now we're presenting it very carefully here, but it does exactly accord with some of the primary school notions that you first encountered when you're doing arithmetic. Is you have this idea of one integer or one number evenly dividing into another one, or cleanly dividing into another number. So let's look at how we're going to phrase it here. So we've got two integers a and b, and we're going to say that the integer b divides a if and only if there exists another integer c such that you can write a as b times. Okay. If that's the case, then we might refer to b and c as factors or divisors of a. And similarly, you can say that a is a integer multiple of b, or it's an integer multiple of c. Okay. So for instance, just some basic examples. So it's true to say that 2 divides 10. Oh yeah, this is the other thing. This is the notation we use. We use the straight line notation. A divides b. The meaning of this is there exists an integer c such that, oh, I've just written it the other, no, b divides a. Write it the same way as it's written on the board. B divides a. So there exists an integer such that a is equal to bc. So 2 divides 10. Why? Because 10 is 2 times 5. Okay. But it is not the case that 3 divides 10, of course, because if you try and write 10 as something times 3, and if this something has to be an integer, what goes there? What's the integer that goes in there? Well, there isn't. So it doesn't exist. So therefore 3 does not divide 10. Okay. So just be clear on that, that's why it's a statement. So this is a statement. 2 divides 10 happens to be true. This is a statement. 3 divides 10 happens to be false. Okay. That's what relations are. They're functions from some set of inputs. Here it's a binary relation, so it's taking two inputs, and the value it's giving you is a truth value. It gives you either a value of true, false. So this one is true because it's not 3 divides 10, so this one is true. But it exactly accords with the childhood notion of one number cleanly dividing another one. Okay. Now, of course, straight away, see there's a big scary box here, big warning. What's the potential mishap to make? The potential mishap to make is to get these numbers the wrong way around, or to read this divisibility symbol the wrong way around. So it's this thing divides the thing on the right. Okay. Or if you think about it, typically you'd be putting the smaller number here on the left. Of course, it is true to say that 10 divides 10. That's true, because 10 you can write as 1 times 10. But typically, it's the smaller bit that's going on the left. So the small number divides into the large number. But every year, I do see people, and it's not so much when you're talking about actual numbers, but when you're building up arguments based on divisibility, people will misquote it and miswrite it, you know, write it the wrong way around. So, I mean, you will know yourself if you have a propensity to make those kind of errors. But it's a clear warning. So you need to come up with some way of ingraining it into your mind that it's the 2 that's dividing into the 10. It's the b that's dividing into the a. So I'm able to write the number on the right as a multiple of the number on the left. Okay. So another quick example: 1, 3, 5, 15. They all divide 15, whereas 10 is not divisible by 3. 3 does not divide 10. Okay. Any questions just about the bare definition? Okay. The beauty of the straight line notation is it's nice and compact. Only takes a second to write it. It's really quick. But of course, the disadvantage of it is you can't tell just, you know, it's not a very meaningful notation. Yeah, it's not saying much. And there's this potential. And especially if you think that it almost looks like a fraction sign, and we're used to writing like 2 over 10 like that. And there you're talking about 2/10. So there you are talking about dividing up the 2 into 10 little bits. So you are talking about kind of writing 2 as a multiple of 10 little things. So it's exactly kind of opposite to, you know, if you think about it, just that 45-degree fraction line. It's the other way around to that. So you can see the potential for getting confused. Okay. But of course, we're mathematicians. We're not just going to be making loads of divisibility statements about particular integers. We're more interested in building up the deeper theory, some general facts about the divisibility relation. And in Theorem 2.1, this is the first theorem we're going to sit down and prove, we've got a whole host of basic, important properties of the divisibility relation. And we're going to prove all of these. Okay? We'll just run through them. So there's 7 of them here. There's kind of descriptive names attached to some of them. Especially the first 2, reflexivity and transitivity. These are common properties that a relation might have. So reflexivity means that everything is related to itself. So here we're saying for every integer, we can write the integer a. You can say that a divides itself. A divides a. That's true for every integer. We're going to prove that it's transitive. Transitive means that if it's the case that you've got 2 conditions, if A divides B and in turn B divides C, then A must divide C. The very first one must divide the very last one. Transitive you can think of as kind of saying that the relation travels through intermediates. So here you've got 2 divisibility relations. B is the intermediate. It takes part in both. A divides B and B divides C. And the divisibility travels from A through B to C. So A is going to divide C. Free is quite an important one, and it crops up all through the course. And this is to do with the divisibility of linear combinations. And here again, there's 2 conditions. If A divides B and A divides C, so you've got 2 integers that A divides, then for every pair of coefficients n and m, every integer coefficients, A will divide the linear combination of A and B. N times A plus n times B plus m times C. 4, 1 divides everything. Every integer A, 1 divides it. 5, and this is 5 and 6 are another occasion where people trip themselves up sometimes. Everything divides 0, and 0 divides only itself. And lastly, what's lastly? Yeah, lastly is a kind of a multiplicative type property that you can multiply both sides of the divisibility sign and it'll still be true. So if A divides B, that's equivalent to saying A times C divides B times C as long as C is a non-zero integer. Any questions about the statements? Just how to read or interpret any of those? I'm going to prove them all now. But I hope you'll agree these are hopefully none of them are surprising or confusing, but they're all basic properties of divisibility, and particularly this one, number 3, will end up referring back to a lot of the time in the course. Okay, so we'll do some work on the visualizer now. Keep ourselves active, and we'll prove all of these. screen. And as we're doing these, we're going to focus on, we're going to try and notice just some of the principles of constructing nice, rigorous proofs, giving very, very clear information, and trying to make everything very, very rigorous and completely watertight arguments. Okay, so these are Theorem 2.1. It's a good first set of proofs to look at. They aren't, none of them will be that long. They're all kind of 2 or 3 liners, or even a 1-liner, some of them. And the key thing to keep in mind, the key thing we're coming back to the whole time, I'll even write it in a different color perhaps, is the definition of divisibility. We're trying to prove things about divisibility. So at the forefront of our minds and right in front of us, if you don't have the book open beside you, make sure it's written down beside you. We're going to constantly be referencing the definition. So the definition says A divides B if and only if there exists a C. Just assume everything is integers such that B is equal to C times A. I've quoted the definition there with the roles A and B are playing as reversed, because before we were saying B divides A, now I'm saying A divides B. Okay, so just be aware of that. But of course, part of knowing these definitions well and being confident with them is never being too attached to the roles played by any of the variables. So you got to kind of understand these things, and like don't get too attached to A is always the small number, B is always the large number. I mean, we can't hope to arrange that or guarantee that. Okay, so let's get started. Number 1, reflexivity. We want to show that for every number A, it also divides itself. And I have an example here. 10 divides 10 because we can write 10 as 1 times 10. Will this idea work for every integer? So here we're talking about A equals 10. The same approach work for every integer? Yeah. Every integer is equal to 1 times itself. Sorry. Yeah, every integer is equal to 1 times itself. So if A is an integer, then, see, the question is, can we write A as equal to something times A? If we can write A as something times A, then we'll have demonstrated that there does exist this integer C. C we're trying to find. And the obvious one is 1. Yeah, that works right. Okay. Therefore, A divides A. A very short and sweet proof. Number 2, transitivity. Now, transitivity, if you look at the structure of the statement on the notes on page 8, it says if A divides B and B divides C, then something. So it's an if this, then that. So the most immediate way to prove those kind of things is to take the this, the if this, then that, assume the this. Assume all that information there. Assume it's true, and from that, try and derive the conclusion bit after the then. So we assume, I won't keep saying A, B, and C are integers, because it's just understood everything is integers. All variables integers unless otherwise specified. So we assume A divides B and B divides C. And the conclusion we want to reach down here somewhere, the 2 gap, is we want to conclude that A divides C. So how do we get from this information been able to conclude that A divides C. So we've got a set of statements about divisibility, and we want to conclude a related one about another instance of the divisibility. Okay. But we're trying to prove things about divisibility, so we need to go back and, we haven't built up a lot of theory about it yet. So everything is going to have to be done just by unraveling the definition. That's the only really way we can make progress. So these conditions that we're assuming, we should immediately unravel them using the definition. Get down to just a simple arithmetic statement about integers. And hopefully we can do some basic algebra using the basic properties of integers, some of those axioms we looked at, although we won't be referencing each individual axiom specifically. We'll just use the common algebra that we understand about the integers to rearrange those statements to hopefully get something that's going to give us this. And we might work backwards first. So how is it that you can conclude that A divides C? How can you make that statement? Well, according to the definition, you can only make that statement if you can show that C is equal to something times A. If we can show that C is equal to something times A, then we'll be allowed to say that A divides C. So what is this mysterious something here? Where are we going to find this integer? Well, we're going to find it, and the only place we can find it is from these two statements here. Because these two statements turn into existent statements about other integers. So surely it's going to be something to do with those. So if these two hold, I'm going to say that there exists an x and a y such that b is equal to xa, c is equal to yb. Okay, everything is integers. I did that without thinking. All I did was unravel the definition. Just write down the meaning of the definition. Don't say that there exists just one C such that B is C times A, well, you can't use C because C is being used here. But don't just say there exists an X such that B is X times A and C is X times B. So there's no reason that it should be the same X involved, the same multiple involved in both. It should be different multiples, potentially different multiples. And now do we know which number is going to go here? Can I fill this gap now? There, can you see it? XY, yeah. YX, XY. Yeah, this is the simple substitution. We've got here, you see, we should start with, if we want an equation C is equal to something, well, here we have an equation C equals something. It's got this B in it, but the B we can replace by X times A, and that brings in the A. When you make this substitution, we see C is equal to XY times A. We've demonstrated that this integer here exists. Why does it exist? Well, it comes from the X and Y. We know the X and Y exist based on the assumptions we've made. Those are correct assumptions. We're trying to prove that these two statements imply that A divides C. So that's good. So we assume this and that, and we include this, so this proves the result. Okay, any questions or queries about that, or about the flow? Just be clear on the flow. We're trying to prove that this and this together imply this statement. So we assume that these two are true. That gives us certain conclusions about the existence of X and Y with certain properties. Then you can roll up the X and Y, and that shows that the necessary thing exists for us to make this statement, that A divides C. Free is very similar, so I'm going to blank freeze the screen for a minute. So try and write out the proof for 3 yourselves, and in collaboration with your neighbors. It's It's very much modelled on that argument for 2. So try and do the same thing for question 3, and we can compare ours and see if they're the same. So question 3 is an if this, then that kind of statement. So feel free to talk about it and discuss it. And so you try and make. It's frozen. A divides B and A divides C. So you assume A divides B and A divides C. Some kind of an argument, and you want to conclude that A divides NB plus MC. That's the gap you have to fill. Be very clear what you're assuming, very clear on what the consequences of those assumptions are. That gives you certain information, and then how you remix that information to get the required result. Remember, the only way that you can legitimately say that A divides these is if you can write NB plus MC as something times A. And it's something really you're trying to construct out of the information given by the two conditions. Does anybody want to volunteer their work? I'll show their work in the visualizer. And sometimes looking at some examples can help. So we could certainly say, 2 divides 10 and 2 divides 16. That's true. Will 2 divide 36? 36, of course, is 2 times 10 plus 16. So that's with n equals 2 and m equals 1. 36 is a linear combination of 10 and 16. Well, we realize it's true, but is it implied, can you also see that it's true kind of a proof? Well, yeah, because the 10 is equal to 5 times 2, and the 16 is equal to 2 times 8. So then the 36, which is 2 times 10 plus 16, well, then you replace the 10 by 5 times 2, and you replace the 16 by 8 times 2, and then you factor off the 2, so it's 2 times 5 plus 8 times 2. 18. Yeah, which is what we expect to see there. The 18 as 36 is 2 times 18. Just want to present that nicely in a general way. So here's my version of it. And really, what I'm doing there is just the general form of this particular argument. So we assume that A divides B and A divides C. That tells us that there exists two numbers, x and y. We don't know what they are, but they exist. B is equal to x times A, and C is equal to y times A. But we do know what they are. X is B divided by A, and y is C divided by A. So that's unraveling these two divisibility statements that were given that we should assume. And we're trying to get to this one down here. So we want to write NB plus MC as some multiple, so this is what I filled in last, some multiple of A. Well, NB plus MC, immediately you can rewrite that using these substitutions here. NXA plus MYA. You see you've got your A, factor out your A, using your... So here is really where we're using all the other integers, or sorry, axioms for the integers, using these properties of distributivity of addition over multiplication. That was one of the axioms. But we won't explicitly reference the axioms. This is just a recognized algebraic property of the integers. So we have indeed shown this linear combination NB plus MC is indeed something times A. Therefore, we can say that A divides it. Okay, any queries about the way I've laid that out, or questions about any of the choices I made there, or? Don't be afraid to put in the bits of English explanation, the introduction, the conclusion. That all helps. It helps structure what the argument is doing. It tells the reader what's going on. Of course, the reader is also you when you come to look at these notes again after a few days or whatever. Yeah, I think the others will can be proved fairly quickly. So what is property 4? Property 4 is 1 divides everything. We let A be an integer. I want to say 1 divides A. The only way I can say 1 divides A is if I can write A as something times 1. What's the something? What fills the gap here? A. So really it's kind of the same equation as up here, but just you're reading something different here. Up here you were saying A divides A. Now we're reading the conclusion 1 divides A. Everything divides 0. So again, we're letting A be an integer. We want to draw the conclusion that 0 divides A. How can you make that conclusion? Well, according to the definition, you can only make that conclusion that 0 divides the thing on the right if you can write... Sorry. See, I've already mixed it up. Here I'm saying 0 divides. The statement is everything divides 0. So I should be talking about A dividing 0. Even I can mess it up. I mess things up all the time. So how do we conclude that A divides 0? Only if we can write 0 as something times A. What is this mysterious number that fills that gap? 0. 0. 0 is a perfectly good integer. So everything divides 0. You can split. If I have no sweets, I can evenly distribute them amongst you all, no matter how many of you there are. Because I'm just going to do all 0 sweets. 0 can always be evenly divided up into any number of parts. But 0 divides only itself. Yeah, because if 0 divides A, then we're able to write A as something times 0. There does exist then there exists a C, according to the definition, such that A is equal to C times 0. But whenever you use an integer times 0, we know that that is 0. So A is everything divides 0, but 0 divides only itself. Then the last one, C is non-zero, then A divides B if and only if AC happens. We let A, B, and C be 3 integers and insist that C is a non-zero one. And we want to show A divides B if and only if AC divides BC. So if and only if means it's a logical equivalence. We want to show that the two statements are exactly the same. And once you unravel the definition of one of them, that A divides B, you'll see the way to proceed. So A divides B, according to the definition, that means there exists an integer D. I haven't called it C because C is already in use for something else. So there exists an integer D such that B is equal to D times A. But that means there exists a D such that BC is equal to D AC. Just simply multiply both sides by C. If you got an equation, you can multiply both sides by some number. That equation is still true. You can also go backwards. If there's a factor of C here, you can cancel it from both sides. Of course, that's the place where we need C to be non-zero. So C being non-zero is important in this equivalence here. If we weren't certain that C was non-zero, we couldn't say that this implies this. Okay, you clear that? Because like 5 times 0 is equal to 2 times 0. We can't just cancel the zeros from each side, of course, because then we have to believe that 5 equals 2. And this statement we have here, this is just exactly the statement that says that AC divides BC. You got the thing on the right is equal to some multiple of the thing on the left. So AC divides. And their equivalence is all the way down, so this is true if and only if that is true. So it's good. Okay, so that's all our parts of Theorem 2.1. So those are good basic properties of divisibility, and we'll be able to continue to build our theory of divisibility in the integers on top of all those things. Now let's just look ahead at a couple of things, and then I'll introduce the exercises to you. First of all, any questions about any of those arguments, or any clarification you'd like on any of those? Okay? Okay. Let's just meet the fundamental theorem of arithmetic. I'll scan those up and put them in a comment on the YouTube video pages. Of course, once we have the definition of divisibility, we can immediately, of course, give the definition of a prime number. I am assuming everybody here knows what a prime number is, but it's worth it just to look at the official definition once again. So our prime numbers are those integers strictly bigger than 1 that have no positive divisors other than the two positive divisors that any integer has, namely 1 itself. Those are properties we just proved in Theorem 2.1. Everything divides itself, and 1 divides everything. So every positive integer has at least 2 positive divisors. Prime numbers are those positive integers past 1 which only have those 2. So 10 is not prime, so it's got 1, 2, 5, and 10. It's got 4 positive divisors. 7 is prime. 7 only has 2 positive divisors. Okay, but everybody knows this already. Those are the first few prime numbers. And a dot, dot, dot here, pretty soon we'll be proving that this list of prime numbers is actually infinite. There's no end to it. Infinite number of prime numbers, and that's pretty the most famous result, perhaps, in basic number theory. We'll be proving that probably next lecture, or in the next lecture or two. Now, we won't be proving until the next chapter this fundamental theorem of arithmetic, but I thought we'd meet it now, get acquainted with what it says. Why are primes so important? Well, one key reason why primes are so important is they're what you end up with when you start with any integer and keep trying to split it into factors. They're the numbers you encounter when that factorizing process comes to an end. Okay? So every positive integer, this is the statement of the theorem, we'll be proving this in chapter 3. It's not immediately obvious, or one part of it isn't anyway. Every positive integer factors into a product of primes. So every integer n will be able to write as some prime raised to some power, some integer power, then multiplied by another prime, say, raised to another power. There'll be some collection of primes that this integer n factors into. Now that part isn't too hard to prove. That is really just comes immediately from the definition of a prime number. Because if your number is, where's my pen? If a large number is not prime, well, you just try and factorize it somehow, 50 times 2. This number you can't factorize anymore. This number you can. 2 times 25. And that has 5 by 5. So you just keep factorizing everything inside, and eventually you end up with a bunch of prime numbers. So 100 is 2 squared times 5 squared. That's the prime factorization of 100 in this form here. It's 2 primes. P1 is 2, P2 is 5, and alpha 1 is 2, alpha 2 is 2. The bit which is a slightly more subtle and which does require some theory in order to get to it is the fact that it's unique. So no matter how you factorize 100, you'll always end up with 2 2s and 2 5s. Now that might seem kind of obvious, and it is a kind of familiar fact. I mean, you wouldn't expect to be able to write 100 as a product of some, like a 7 times something else, There's something inherent about 100 that it's only 2 and 5 are the possibilities there. But what if you had this factoring tree isn't unique? Because I could have started to build a factoring tree a different way. Just said 100 was 4 by 25. So there is some choice involved, and if you've got a large integer, by large I mean taking up more space than there is in the universe to write it down, but just some large integer, you can imagine there's an unimaginable number of different ways of constructing a factoring tree. So how can you be sure that you'll always end up with the same collection of primes at the end and the same collection of exponents on the primes? So that's this uniqueness part. And that does require a bit of theory to build up. Okay, so that's the big result we're going for in chapter 3, and that's the reason why we're going to discuss what we're going to discuss in chapter 2. So this is the only lecture for this week from me on number theory. You'll have 2 cryptography lectures. But on Friday, you'll have your number theory tutorial with me. And there we'll tidy up any remaining issues about induction. So please come armed with any questions you have about those. And if you look at the end of chapter exercises, which are so there's a few exercises scattered throughout the chapter. But if you just go, sorry, I'm losing my mind here a bit.
Yes.
Yeah.
It's like a,
You used to do it, yeah.
it's like a cash prize. The next one.
Yeah,
Sorry, so here, exercises 2.3. Just before you all disappear, just got 2 minutes. Exercises 2.3, these have a few exercises here that are only talking about divisibility. They're not talking about the common divisors and so on, which is the next topic. So questions 1 to 5 there. I think all of those are open to us. Just questions about divisibility, so you should prepare those for Friday's tutorial as well. Do come ready to discuss these. And there's 3 more induction. I'm not giving too much away to say those are proved by induction, because they're infinite number of statements indexed by the positive integers, but they're all about divisibility statements. So have a go at those as well, and we'll clean those up on Friday as well. Okay?
You wanted to say, I didn't